The birth of matter, how protons and neutrons formed in the early universe. Imagine the universe in its infancy, not as the vast cosmos we see today, but as a superheated, rapidly expanding soup of pure energy. This primordial state was the crucible where the very building blocks of matter were forged. From this chaotic beginning, a dramatic transformation occurred, the formation of protons and neutrons. These particles are the foundation of every atom, and therefore, everything we see around us. This process, known as Bang Nucleosynthesis, is a cornerstone of modern cosmology. Understanding it unlocks profound insights into the universe's origins and evolution. In the immediate aftermath of the Big Bang, the universe was far too hot for stable particles to exist. Energy reigned supreme, constantly morphing and fluctuating. As the universe expanded, it began to cool. This cooling process was crucial, as it allowed energy density to decrease over time. This decrease in energy density paved the way for the formation of more stable structures. The universe was transitioning from a state of pure energy to one where matter could begin to take shape. Protons and neutrons aren't fundamental particles themselves. They are composed of even smaller particles called quarks and gluons. In the early universe, quarks and gluons existed in a free state, but as the universe cooled, these fundamental particles began to coalesce, drawn together by the strong nuclear force. This process, known as quark confinement, occurred within the first microsecond after the Big Bang. It was a pivotal moment in the universe's history. The exact mechanisms of quark confinement are still not fully understood by physicists. It remains one of the most challenging and fascinating areas of research. As the universe continued to cool, energy levels dropped further. This allowed quarks to bind together more stably, forming composite particles called hadrons. Among the most important hadrons to emerge were protons and neutrons. These particles would become the nuclei of the first atoms. A proton is composed of 2 up quarks and 1 down quark. These quarks are held together by the strong nuclear force, mediated by gluons. A neutron, on the other hand, consists of 1 up quark and 2 down quarks. The slight difference in quark composition gives neutrons a slightly higher mass than protons. The formation of protons and neutrons was a crucial step towards the formation of atomic nuclei. Without them, the universe would be a very different place. In the early universe, protons and neutrons could readily convert into each other. This conversion was driven by interactions with other particles, such as electrons and neutrinos. Initially, there was a state of equilibrium between protons and neutrons. The rate of conversion from protons to neutrons was roughly equal to the rate of conversion from neutrons to protons. However, as the universe cooled, this equilibrium began to shift. The formation of protons became slightly favored over the formation of neutrons. This shift was due to the fact that neutrons are slightly heavier than protons. Therefore, more energy was required to create a neutron than a proton. About 1 second after the Big Bang, the universe had cooled to approximately 1 billion degrees Kelvin. At this temperature, the conversion between protons and neutrons began to slow down significantly. The ratio of protons to neutrons stabilized at roughly 7 protons for every neutron. This ratio was critical for the subsequent formation of light elements. If the ratio had been significantly different, the composition of the universe would be drastically altered. The formation of stars and galaxies might not have been possible. This precise ratio highlights the delicate balance of physical laws that govern the universe. Even slight variations could have profound consequences. As the universe continued to cool, protons and neutrons began to fuse together. This process, known as Bang Nucleosynthesis, resulted in the formation of light atomic nuclei. The primary elements formed during this period were deuterium, helium-3, helium-4, and trace amounts of lithium. These elements are the building blocks of the first stars. The most abundant element formed was hydrogen, which is simply a single proton. Approximately 75% of the universe's mass was in the form of hydrogen. The second most abundant element was helium-4, making up about 25% of the universe's mass. The remaining elements were present in only trace amounts. The formation of protons and neutrons, along with Bang Nucleosynthesis, were pivotal events in the history of the universe. These processes laid the foundation for everything that followed. These early events set the stage for the formation of atoms, stars, and galaxies. Without them, the universe as we know it would not exist. The abundance of light elements observed in the universe today provides strong evidence for the Big Bang theory. It is one of the most compelling pieces of evidence supporting our current understanding of the universe's origins. Studying the formation of protons and neutrons allows us to probe the universe's earliest moments. It provides a window into the extreme conditions that existed shortly after the Big Bang. Understanding these processes is crucial for unraveling the mysteries of the universe. It helps us to answer fundamental questions about our place in the cosmos.